access to it. All right. There we go. Up and running. I will attempt to keep an eye on chat as well. That way I can see questions as they come up. So you guys were roughly here from the notes that I've got. Okay, there we go. So we have a couple things going on all at the same time. We've already had a lot of lecture time back and forth today. Having to take over all these classes. All right. Time temperature transformation and then continuous cooling transformation is what my notes say. Does that sound familiar to everybody? Yeah. Okay. So these are where we have a couple different pieces of information all in the same area. So what we've got is we've got some what are called isotherms. Long story as to what those are, but the details aren't super important. These are time temperature transformation plots. So what these are telling us is think about this. Really the best and clearest way that I can explain it is like this. Take something like this particular composition here. At a given composition C0, let's say this C0 is this particular weight fraction. You guys have seen how we're going to actually do calculations as far as using the lever rule and our tie lines in order to calculate what the fractions of each of these things are, right? What you're doing with these time temperature transformation curves or these constant cooling temperature curves is you're taking a slice out of this graph at a specific composition as if you're taking a book off of a shelf, right? So this is something that allows you to take that book off the shelf and sort of turn it sideways, open it up, and look at the information. And what that is, that extra dimension, the depth in the bookshelf is time. So depending on how this is used, especially with what kinds of alloys are being used, you're looking at this temperature graph, and you're looking at, for instance, in this case, the transformation graph. So this one is the TTT, the time temperature transformation graph. They're not super helpful. You can see where they relate and correlate to these constant cooling curve graphs, but the information doesn't translate as cleanly because it will tell you, you know, here it was where we pass through this phase envelope. We start forming the austenitic phase. We transition or start transitioning from the unstable austenitic phase into the perlite phase if you just hold it at a constant temperature of, in this case, 675 C. So that isotherm allows for the formation of perlite grains exclusively at that temperature. So, but it takes a long time to actually get there. And that's what we're looking at. So we're going to spend more time in these CCT curves and really understanding what they're all about. So starting from that eutectoid temperature, so where we start having the phase change into whatever the first phase change really is with biphasic or multiphasic behavior for any given composition of something, we look at this and say, okay, based on this, up above 700, and we'll be able to see this in a graph coming up where it's easier to see side by side. Below that, you have a mixed phase in here, and at a certain temperature, or as you cool off, depending on how long that takes, you have to transition through this region anyway. The rate at which you go through that transition changes what the composition or what the ratios are. So there's a lot that goes into the information in these curves, what the mathematical realities are having to do with surface energy interactions and all kinds of complex thermodynamic stuff as far as how these curves are created. But they're designed in such a way to be able to represent the information so that we know what the phase changes are. So if you drop down suddenly to 650 or 640, whatever this is, and hold it at 640. So if you rapidly drop to 640, you suddenly open the door of the furnace and drop the temperature down to about 640 and hold it there, because that's the internal temperature that's maintained in the oven or something like that. Then cutting all the way across, you're going to start forming perlite here. You're going to reach the 50% mark, and then you're going to reach the 100% mark at the other side. And so each of these curves represents a concentration of perlite or percent conversion from austenite to perlite. So over here, no austenite exists, no gamma phase crystals. So this is what it looks like originally during nucleation. So nucleation starts right at this edge, and we'll see some, I think you guys have maybe seen some images. We'll see some more additional examples of this. And then as perlite starts to form, about half and half, then all perlite is formed at that temperature. So the longer it's there, it very quickly forms the perlite. So let's take a look at an example here that's a little bit more complicated. So this one, there were a lot of questions about this in this morning's lecture, and so we'll spend some time trying to make sure you guys are understanding this one, because it's pretty important. So the transformations that come from a non-eutectoid composition, so anything that is not at this point right here, right, is going to have a combination of gamma and cementite, right? So austenite and cementite. And just like up here where you have austenite in liquid inside this phase envelope, or you have cementite in liquid in this phase envelope over here, you have the eutectic point here, so the lowest melting temperature. We're going to learn why that eutectic point is actually interesting and why we're interested in composition, because we're going to talk about the way that we work with and process materials in 11. So since we're going to try and get you guys caught up today, I'm not going to go into that here. We'll go into that when we get there in 11. Key things to understand about this graph, the CCT graph here. There are a couple different phase envelopes. So everything to the left side of the purple curve is all austenite. It's all gamma phase crystals. As you pass through that at any given temperature, at that boundary, all the way down to about 600 or so, where you no longer form anything other than perlite immediately. Everything below about 600, you start to form perlite immediately, or we'll find out another thing that you form here in a couple graphs. The phase envelope allows you to start having cementite and austenite together. So alpha plus the alpha, or in this case, we have gamma and cementite, to be more accurate here. Alpha we're going to get to in just a second. So we have cementite and austenite, and that's what the C and A are. So these are the things that you're going to see on homeworks, and these are going to be particularly useful to you guys. So this is what I mean about basically at a given composition, you're taking this slice out of the temperature composition graph, the phase diagram. You're taking that slice out of the phase diagram and opening it up like a book, and that's what this is. So somewhere below, just a little bit below like 900 is where you start to have that phase transition from austenite to austenite and carbide formation. Just a little bit below 900 is where that starts to happen. So the lower you go in temperature, the lower you reach until somewhere around 727, somewhere down here at 727, where you start to form this other phase. So this line and this line are the same thing on these graphs. So as you further cool down below that range, you start to convert the gamma, the austenite, into alpha or ferrite. So this is just normal iron that you convert into. But you do that by way of a transition through perlite, because that's where your cementite goes. The cementite gets sort of interleaved with the native alpha crystals, and so you form that combination that is perlite. And perlite is a little harder than, it was considerably harder because of the presence of that carbon, than the natural ferrite is. And think of it, because of just the actual structure of it. You guys have seen it, but let's look again quickly at an image. Yeah, kind of here, but it's a little better represented here. So think of these crystals, these particular perlite crystals, having these cementite bands. Think of it almost like a deck of cards or a phone book, right? Something with a lot of layers stacked in the same direction. You can bend it, but trying to tear or shear that is very, very difficult, right? When all of these layers are present, you have a lot of resistance to movement. Bending is reasonable for something like that, but the actual structure of this grain is such that it doesn't really want to compress as readily, whereas just the natural ferrite itself, those grains are much more able to move around and slip. There's other factors like the kinds of crystalline boundaries and all of those sorts of things, but that's why these are important and why the grain nucleation is important on these. So let's get back to, here we go. So as you transition through these phase boundaries, you get more and more of that perlite, so more and more of those stacks of almost like plates of carbide, in a way that prevents it from wanting to shear and twist and move as loads and forces are being applied to those materials. So there's a lot of different factors that go into what the material behaves like. So as you go to cool, you also, below that range, when we go farther down, you get into another kind of structure called bainite. And this is a combination of kind of shorter abbreviated strips, so it's not the stripy zebra looking pattern of perlite. It's more individual strips that are much narrower of cementite next to zones of alpha ferrite. And what that tells you is, especially for something like this at 0.76% weight percent carbon, you have a very for any length of time, really almost at all. Talking about this is 1 second here in terms of time. So anything below this eutectoid temperature at even 1 second, as if you're cooling at all, you're about to hit this perlite boundary, because it's not going to cool very quickly. It's going to have sort of an arc if you're just air cooling, right? And it's going to be maybe a little bit steeper at first, and then it's going to kind of level off. And so you're going to end up somewhere within a handful of minutes, you're going to end up in this phase where bainite is going to exist for that particular isotherm. So that's what these letters mean on the graph when you have to go to identify these later. So austenite, perlite, and bainite are the keys there. So for this particular isotherm, drop it quickly down to this temperature, 640, 650, whatever this is, probably about 640. You come across the line with perlite formation. But if you drop below that temperature range, below this boundary, you get bainite formation. So the way in which the cementite is collected together changes because the different temperature. Remember that temperature is just the physical kinetic energy of the actual molecules of the metal, right? So in order for something like the carbon to diffuse, it has to It has to be able to move around, move past the other things. And the crystalline structures are so solid that they have to be at elevated temperatures in a lot of cases to allow significant motion of any grain boundaries and things like that. So this is why we have to heat them to such high temperatures. They're physically heavier atoms than something like water. They have to take a lot more kinetic energy in order to be able to get past each other. And that's why you have to hit these materials with a lot of force to get them to move, right? Unless they're very, very thin in profile, they are very strong and resistant to bending. So some of that comes from the grain boundaries. Another type of microstructure that can be formed, but it takes a very long time in order for this to happen. This is more of an equilibrated type of structure. This is held at a more elevated temperature for a much longer period of time, usually more than 24 hours at a specific temperature. So it's bainite or perlite at these temperatures, right just below the eutectoid for a very long time. And the driving force for this is surface energy minimization, is what it's called. It's a thermodynamic driving force. It's the same kind of thing where when you put oil in water and you vigorously try to mix it up, it doesn't actually mix, right? You get lots of these little bitty droplets forming, but that has a very high surface area. It's very unstable, right? If you put in something else to change those surface energy interactions, like, for instance, mustard powder is a common emulsifier for foods, what that does is changes the surface energies by changing the chemical composition of those surfaces, and you can stabilize emulsions using that particular material. So it's used in a lot of sauces for that reason. It's used in some curries and some other things to help stabilize that emulsion. Same kind of chemistry that's going on here, just much higher chemical energies involved and much higher temperatures involved, because everything has these such stronger bonds and physically more mass, and they don't want to move around. So they behave as solid solutions rather than liquid solutions. So it's important to understand that aspect of the chemistry that's involved, because that driving force is what causes droplets to come together and merge. There's a ripening effect. There's a bunch of other particular terms that apply to that, but it's the same kind of idea of it wants to minimize the surface area interaction, and in this case, the small droplets have a lesser surface area than all of the long stretches of curvy, windy, plate-like structures that the cementite forms in perlite. So the longer you let it run, the more it minimizes into whatever the minimal surface area is, and that happens to be a sphere, because it's just a mathematical representation of the minimum surface area for a given volume, happens to be a sphere. It's a mathematical necessity. So spheroidizing is a process that's used, and we'll talk about it in 11, about it's the formation of these almost droplet-like shapes in order to make it so that the material is easier to work with. So this is an equilibrated type structure that allows for much more easy motion of the grains past each other. Think of them as sort of rolling along each other like ball bearings almost. A lot easier to move, a lot easier to work with, a lot easier to machine and do things with than a non-equilibrated or uneven type of material. So we'll talk a little bit more about that distinction. But in any case, you're trying to start from something like coarse perlite, and any kind of heat treatment that you're doing using the principles from these phase diagrams is you're trying to convert over here to fine perlite to make it a little bit harder, or you're trying to go for an intermediate material and trying to head for bainite, or you're trying to head for spheroidite to make it easier to be able to machine and make the behavior more uniform so that you're not having different pockets of the material that are harder or softer in different areas, because that can make it tricky if you have a very intricate piece that you need to machine in one corner of something that you're milling out, and then all of a sudden the material is changing hardness all the time. It's going to be very hard to get an even machine on that surface, right? So it's about equilibrating the material so it's easier to machine or process, and then you're going to reheat treat it to form perlite again or something like that. So there's a few different paths that this process can take. The slow cooling path gives us perlite and proeutectoid phase. So that's proeutectoid alpha or ferrite. There's a moderate cooling path that is that'll take us to bainite, and so that's a little bit more aggressive of a cooling slope. So maybe it's air cooled, taken out of the furnace, and so it's cooling off a lot faster, but it's still kind of moderate. And then there's the rapid quench that happens, which forms martensite. And so we're going to take a look at what that looks like and why, when we form exclusively martensite through a rapid quench process, why that needs to have a reheat as well in order to temper the material. So a couple things to really understand about this is everything is a cost trade, always. Martensite is at the very highest end for strength in terms of grain structures for the given material. Tempered martensite is a little less strong and slightly more ductile. Bainite is somewhere in the middle. Fine perlite, so small grains, stronger than coarse perlite, which is large grains. And then spherodite is the least strong, but also the most ductile. So we need different levels of ductility and strength for different applications, right? And we'll talk about, when we look at some of the grain structures of martensite specifically, why you don't want to use something like very high martensite containing material for something like a bridge or something that has to take abuse. You want some level of ductility there in order to have some forgiveness in the design criteria, rather than brittle fractures and failure. It's explosive failure often without any warning. It just bears under the load, then suddenly explodes, right? Think back to the tension lab. Was any of you standing close to the machine when something like that 7075 aluminum let go? A pretty sharp bang, right? So it's just loading, explode. Like there's no, like you might hear a ping or something right before the material lets go, but probably not, right? You can't imagine yourself, or you don't want to imagine yourself on a bridge and all of a sudden you hear ping, bam, something like a gunshot, and then all of a sudden you and all of the other drivers are in the water, right? That would be really bad. So we don't use high strength materials to the same degree in something that needs to take a lot of abuse. So there has to be a mix of materials that are ductile. Whereas the bolts that are holding those together, you want those to be pretty high strength. And so there's kind of a balancing point there. So we'll talk a little bit more about some of the aspects of these. The structure here, because I know you guys have covered at least a little bit about the cubic structures. So face-centered cubic, the body-centered tetragonal, which is what this BCT is very different. It allows for a lot more open spaces in order to be able to hold on to the materials, in order to allow for diffusion of carbon. There's a lot of potential sites for carbon atoms, so these can take a lot of and store a significant amount of carbon in this particular structure. But there's some interesting things about this particular crystal structure as well that gives it the properties, right? So you can see on the right side, these are like sharp shards just all going different directions. So if you imagine trying to apply a force and then squash those materials, it has support going in all three dimensions, and it's just not going to want to move or shift. All of those jagged edges have extremely high energies associated with them trying to move or slide past each other, simply based on just the principles of friction alone. So there aren't a lot of directions where there's slip planes and things for these to move past each other and alleviate stresses, right? Whereas you saw some of the steel samples that fractured on a diagonal, you saw those slip planes actually form, and the material slips and slips and slips and slips until it finally doesn't have enough energy to maintain connection and then releases, right? So they were always diagonal, and that's those slip planes showing up. These materials, these martensites, don't have that to the same degree. So that's why, like that hardened steel is a much sharper shard kind of fracture than the kind of even cup and cone fracture of a mild steel. So it's because of this particular grain structure. That's why it separates and is jagged the way it is. So in order to reach that martensite exclusively, you have to go from very high temperature in pure austenite all the way down to below a couple hundred within, on the order of 1 to max couple of seconds. So it has to be very, very fast. And this is part of the reason why when you're seeing somebody that's doing blacksmithing on a blade or something, they're going to tell you, if they're in the process of doing any kind of useful education, I have no idea if I actually got the right, if I actually got what I think I got until I go to actually test the material, right? I can't just tell by looking, oh, I got a lot of martensite on that one, right? It's not obvious. It has to happen very, very quickly. They have to have a very sharp temperature drop, several hundred C, in a matter of 1 to 2 seconds. And this is why they use something like oil to do it, is they very quickly get down into the martensite region. But depending on, if you take even 3 or 4 seconds to get into there, to get it below those temperatures. So if you pick it up out of the oven and it's cooling off and it's cooling off, and then you quench it suddenly, you're going to fall through the perlite and bainite regions. And so you'll have a little bit of hardness, but it's not going to be as hard as it would be otherwise. And so you guys are doing in lab the Jomini end quench test. So you're going to see the example of the end being much, much higher in hardness compared to the stuff that takes longer and longer because of how it's passing through this curve. So this is where some of those principles come from. Couple key points to note here are that the martensite transformation has to be rapid and diffusionless. That's why it's so severely unequilibrated, is really a good term to do this, because it looks chaotic because it is. Things are just trying to rapidly find a place to solidify, and it just happens to solidify in a chaotic form that's very, very strong. The percent transformation depends on the temperature that it was cooled to and how quickly. So how quickly did it get down below 200 will tell you the percent composition of martensite versus bainite or perlite, depending on how quickly it happened. So the martensite formation looks like a slow cooling process. It can be a slow cooling process to form alpha and carbide, or alpha and cementite. The quench is what actually gives us not the face-centered or body-centered, but this body-centered tetragonal that will change the way that it behaves. Because this is diffusionless, because there's no equilibration, there are very few slip planes, meaning this material is very, very, very hard, but also very brittle. right? So if you take a material like this that's very hard and a very good cutting edge, but then you try and load it from the side and you try and bend it, it's going to be very resistant to bending. And then just like in the tension test, it's going to let go suddenly and explosively. And it's probably going to shoot shards everywhere. So that hard, brittle fracture is dangerous in terms of like structural loadings and things, because that's actually very bad. So we don't want that kind of behavior in structural materials typically. We do want them in tooling and areas where being brittle is okay because you need such a high hardness, right? How do you machine steel with harder steel? How do you machine something like diamond? You don't do it with steel. You have to do it with something equally as hard in the surface, because if you tried to machine hardened steel with mild steel, you would just dull out the mild steel, and the hardened steel, like if you were to try and use a mild steel drill bit, it would wear out very quickly, right? So, and dipping it in titanium nitride like the Chinese often do doesn't make them a better drill bit. Like it's you can coat it all you want, but the underlying material is not strong enough to support what the coating could allow it to do if it was properly tempered and hardened with enough martensite underneath. So this is why these principles are pretty important. You temper it back to including some alpha and carbide by warming it back up, but not nearly up to that eutectoid point. You just warm it up enough to allow some diffusion to actually take place, and that tempering gives you a little bit of ductility back, so it's not as prone to just shatter the instant you hit it with, especially like an impact or a sharp loading. So any questions so far? It's been a lot of materials and it's going to go fast, but this is why I'm trying to get you guys caught up and why I'm recording. I haven't seen any come up in the chat. Okay, so I'll keep an eye on chat and see if any do come up. More on the effects of adding in elements. As soon as you add in other types of molecules, in this case, things like chrome, nickel, molybdenum, silicon, manganese, all of these change the way that this phase envelope is positioned on the phase diagram. So, or on the CCT diagram. What it does is it changes how the phases behave and what these phase envelopes look like, such that you have a much higher time limit, for instance, before you pass through the beginning of perlite formation. So especially with things like chrome, nickel, molybdenum, often those are together in different ratios for hardened steels. So these are grades of steels that we'll learn about the nomenclature a little bit later, but you may have heard of, especially in like racing applications or aerospace applications, things like, oh, it's made of a chromoly steel. That's a really expensive material to work with, but it's a really, really good material because it has a broad range of time compared to some other things to be able to actually get the desired hardness and the desired grain structure. So it can have a little compliance with some bainite formed and some martensite, or you have a little more time to be able to actually quench it into the martensite only region. So depending on how you transition through, you get different types of behaviors of the material, and that broad spectrum allows you to fine tune how you want it to behave based on the heat treatment. So that allows you to customize exactly how it performs in a specific application. So just because it's a chromoly steel doesn't mean it's the same ratios, doesn't mean it's going to behave exactly the same as another chromoly steel that's been tempered and quenched differently. So the eutectoid temperature is still the same because it's still steel. But because of those alloys, you also have some degree of the ferrite formation that happens up above that eutectoid temperature. So it changes some other things about the phase diagram, but we're not going to dwell on that really any more than we have to, because we're mostly concerned in terms of hardening and tempering materials about where this martensite transition happens and what percentage that is. So you want to try and get down to this 90% as quickly as possible if you want a high degree of hardness. And so you have a pretty good range in order to be able to do that, almost 100 seconds versus like 1 or 2 seconds, which is really good. So the reheating is a really, really important part of this. And this is why, depending on what you're trying to do with the steel, the ability to do the heat treat and change it is really important. And the processing that you're going to do afterwards also has that in mind. So there's a few example problems that we can take a look at that I think will be helpful for you guys. So another phase diagram, we'll say this one is tin and lead. At 220, we're going to draw our tie lines and use our lever rule. So it's going to look something like this. At this composition, 40 weight percent tin, 60 weight percent lead. We have an approximate reading here for C alpha. So concentration of alpha or ferrite is 17 weight percent. Up here, the S line gives us 46 weight percent for our beta phase for our lead. So those two together give us what we need in order to put into our calculations, right? The R divided by the sum of the two give us the weight fraction for that phase, for the alpha phase. And then the balance of one will be liquid. So this one, because of where it's positioned, the majority is going to be alpha. And so looking at that, this is what we would expect to see. So this gives us the alpha is at 17%. So our alpha, or the majority is the liquid phase, with the balance being alpha, because of where that because of where this tie line actually lands. It's a lot physically closer to the liquid phase than it is to the alpha phase. So that distance is what you're looking for to determine, okay, did I do that calculation right? So closer to the alpha phase, closer to the liquid phase. Closer to the liquid phase looks like about 80% ballpark. Yeah, turns out to be about 80% and 20% alpha. So does that make sense? Okay, on the grand scale of clarity, we have like mud. We have below that dry dirt, dry dusty dirt. Above the mud, we have like OG Gatorade flavors and lemonades. Then we have above that, we have like some Crystal Light and stuff that aren't real drinks. And then we have flavored waters and then holy water at the very top. Where are you guys at on that scale with regard to phase diagrams and tie lines? Okay, good. Let's see, a fair blend of Gatorade and Crystal Light, roughly. Okay. And then there's a 6, of course. Always got to be that guy voting turnip in every election. It's okay. I can work with turnip. We're going to look at a couple more examples, which should help with that. So let's take a look at a 0.4 weight percent carbon steel. And we're going to look at a temperature just right below the eutectoid point. So we're going to pull a couple key numbers out of the graph that are going to be important for you guys to know for later. So the amount of actual cementite that forms. So we're looking first for the composition of the carbide and ferrite. So what are the ratios? What are the rate fractions? Then the amount of cementite in grams for 100 grams of this steel. and then the amount of perlite and the proeutectoid ferrite that's going to be in that 100 grams. So what does that look like, and how does that form overall? So the perlite is going to be interesting because these two are not going to be the same number. They can't be mathematically, but it'll maybe make some more sense why. So we're going to use the RS tie line just right below this eutectoid point, and we're going to use the fraction. So C alpha right basically just below this. So infinitesimally below, or 729 or 726.99999 degrees C or something. Our alpha is, for the concentration of pure alpha, is 0.022. So that's just a number that you need to know for later. The composition for cementite is going to be over here at 6.7, not like 100%, because there's other things that happen on the phase diagram way out here. We're not going to get into those now. Just 6.7 is where the world ends for iron and iron carbide. You start getting into other phases and like charcoals and other stuff when you go really high in carbon percent. So we're not going to talk about those. We're going to focus in on just the low weight percent for this phase diagram. This stuff gets pretty ugly over there. We're going to look at, with those two, calculating from here. We know where our C0 is. So our C0 is this 0.4 weight percent. So we calculate using the lever rule. The difference between this R is the difference between C0 and C alpha, right? Mathematically, it has to be. Then the S mathematically has to be the difference between the iron, the 6.7, and the C0. In this case, they're using the C alpha. Arguably, it should probably be C0, but this is one of the things that's important to understand. So this 0.4 minus our 0.22 for the alpha phases. This is the formula that you have, but we also have to add in the R, and that's part of the reason why it's not actually C0, just to clarify in case some of you are going to get confused on that point. Because you have to add in the R here, you take the same thing, and so you have this example where it would be the carbide minus C0 plus C0 minus CA or C alpha, and so the C0s cancel out and you're left with C alpha. So it is a mathematical necessity. So don't allow yourself to get confused on that. But that allows you to get the information about the phase composition. So we know the weight fraction of the cementite at 0.057. Taking that, we know that 5.7 grams out of this 100 gram sample is going to be cementite. So for part Z, we're using the VX tie lines. So the VX, again, going back to just this portion below the eutectoid point, and trying to understand what that version is. And so in this case, just above the eutectoid point, just barely above. That's why we have to have the VX. We don't have the RS. So C0, we know, is at that 0.4 weight percent carbon. We know C alpha, and we know the C perlite. So C gamma is 0.76 weight percent carbon. So that's at this eutectoid point. So we put that into the formula. So this time it's C gamma minus C alpha. So our 0.76 for perlite minus the 0.022 gives us a weight fraction of 0.51%. So based on this, we should expect, again, roughly halfway between the two. Sanity check should be about 50%. You get 10%, 5%, go back and double check that you didn't drop a 0 somewhere, enter it wrong in the calculator or whatever. And of course, by calculator, I mean Chat GPT, because nobody does their own homework anymore. So the amount of perlite in 100 grams is that weight fraction times the 100 grams, giving us the 51.2 grams. All right. Any questions on that one? Is that making sense? A little bit? The more and more examples you do, the better overall this will start to make sense. So there's a couple of other things to quickly cover that'll help clarify a little bit in regards to the CCTs. I wanted to go ahead and include these because I think some of these principles are pretty important, especially for the review of this chapter as a whole. And then we can get into a little bit into chapter 11, and then we'll hopefully be able to finish 11 by the end of class on Friday, because we got to get through that material. So the heating process as it goes through the eutectoid formation allows for the rearrangement of the face-centered cubic into the body-centered cubic, and then some clusters of the cementite remain. And so they have different packing arrangements within the same overall material. So one of the big questions is, sparked a lot of kind of additional conversation this morning, was are the mechanical properties of a non-equilibrium structure more desirable than an equilibrium one? What do you guys think? So are the mechanical properties of a non-equilibrium structure more desirable than equilibrium ones? Anyone brave enough to hazard a guess? Who thinks old school Star Wars and it's a trap? Okay, we've got a non-equilibrium vote. Equilibrium.
If you're not in equilibrium, does that mean that the properties are going to change like while you're using the material?
It means the properties are going to change throughout the material, just like this example where you have ferrite here and you have cementite here, right? So one of these is hard, one of these is soft. So if you imagine like a cutting bit physically running through these molecules, right, trying to separate them out, the ferrite is going to catch the bit and cause friction, or the cementite's going to catch the bit and cause friction. The ferrite is just going to sort of melt like butter against a cutting tool, right? And so what you have is, in the case of something like machining, you have unevenness in the materials, and that can screw around with your tolerances if you're machining in a way that's, hey, only spend a few seconds on this path, right? You're making some assumptions about the behavior of the material under the cutting bit, but if your hardness throughout the material is going up and down, that could be bad, right? So depending on what
there are situations where you would, sorry.
Go ahead.
So are there situations, I mean, I'm having a hard time thinking of it, but are there situations where it would be good? I would assume generally you would want equilibrium so that you know what you're working with, but are there situations where you would like selectively machine or like make a material to be in a non-equilibrium form for like a project?
Yeah, so one of the examples of that is the martensite, for instance. So if you want something that is, because there's always a compromise between ductility and hardness, or what we think of as strength, right? Because there's all these different terms and materials mean different things. Strength has to do with things like tension and loading, and how much force, specifically how much force the material can take before slip planes slip, before defects propagate, right? That's strength. Toughness, do you guys remember what that is? It's a very key word, very important word in materials. You guys remember?
It's impact resistance, right?
Yeah, it's basically impact resistance. It's the total area under the stress strain curve, right? So material that's has a very high tensile strength, but does like the 7075 aluminum, goes up, 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 break suddenly, doesn't necessarily have a lot of area under it. The steel that's stretching and pulling and slip planes are slipping and slipping and slipping and slipping, and then it lets go, is very tough because it takes a lot of abuse before it actually lets go and releases. You get a lot of warning, you get a lot of yielding behavior, so you get a lot of abuse that it takes before it finally fails. Really high hardness materials are great for things like cutting edges, but they do that at the cost of, because they're non-equilibrium materials, they're non-equilibrated, they are by definition, they are all of those sharp shards going every different direction. They're creating a circumstance in which the material is resistant to being worn down. The surface is extremely hard, but if you hit it on a sample, so if, for instance, you're trying to machine something and the bit hits a corner of a material while it's spinning, or while it's not spinning at the right speed or whatever to cut through the material, that'll oftentimes chip or break the bit because it'll fracture, it'll shatter. So it's a very good bit for machining, but it would make a terrible hammer, right? You can't make a hammer out of something that's brittle. You need something that's tough and can take a lot of abuse, because it's designed to smash stuff with a lot of force, right? So different applications actually require different mechanical properties. Those change with not only the temperatures and times of processing that we're talking about here, but also the method of which we're processing, right? Because you guys did the welding lab, you saw heat affected zones and discolorations in the steel and all of these other things. All of those properties matter in terms of how the material behaves. So that stuff that got heated up got softer. So a weld is actually weaker than the surrounding material almost always. There's almost never an exception to that. There can be welds that are stronger, but that's often because they have additional buildup of layers. And so I've seen some people do some crazy, like almost braided weld techniques. But what they're doing there is they're building up, a half inch of weld material on something. And now, sure, it's stronger than the surrounding material because it's physically thicker, not because, but there's also more heat affected zone and all kinds of other things. So everything in material science is a balance or a compromise. You gain something, you lose something else. And for the purposes of understanding the transformation, the nucleation part is very, very quick. It's a long time to actually have the growth of those crystals happen. This is why we have to heat the samples for half hour, 45 minutes for doing this Jomini end quench test, is to make sure that we get complete growth and nucleation, beyond the nucleation, complete growth of the crystals in that austenitic phase, so that when we go to quench, we actually have some of that material that plummets down into the high martensite region. Then it forms as you go further and further in the material, as you go further away from that quenching end, you see the kinds of effects of this. You see the recrystallization rate at these lower temperatures. The transformation happens much more slowly on a slow time scale. This particular one is for pure copper, rolled copper specifically. As you go up in temperature, you get recrystallization, but lower in temperature, it takes significantly greater, or many orders of magnitude more time to grow the recrystallization than it would. So that rate is said to be 1 over t to the half. So that's taking the slope at the midpoint is the approximated rate of recrystallization of something. So it's often so slow that actually achieving equilibrium state in the material is not always possible. A lot of reasons for that, one of which is you don't always get perfect diffusion. You're not always going to get perfect equilibration. You're not always going to get movement of the material. You can kind of get there more quickly, but it's going to asymptotically approach the finished state. And some of these at lower temperatures don't even really do a good job of asymptotically approaching, like at the 135 does. So this was very rapid, but anything below that, especially like 88C, you're nowhere near absolute equilibration here. Even though it looks like it's at the top of the chart, your actual approach to this 100%, you're literally never going to reach it at these lower temperatures. So you're always going to have defects. You're always going to have issues with some of these crystalline planes. So undercooling, I don't know if you'll actually see that term. I haven't had a chance to look at the 10 homework at all myself, but I have had a chance to look a little bit into the 11 homework. I don't know that you're going to come across that, but undercooling is just trying to describe cooling below the transformation point at the eutectoid temperature. So anything below that 727 is undercooling the material for a given composition. So in order for that transition to happen for gamma to transition from gamma from the austenite into the ferrite and the cementite, you have to be below the temperature, which is sometimes referred to as undercooling. So you might see that term, you might not. I just wanted to make sure you guys had seen that. For the eutectoid transformation, this is the way in which these grow, and the reason why is because between these grain boundaries here for the austenite, you have the ferrite form, and then you have, because of the surface area minimization, you have the carbon being less soluble in the alpha phase. So it's being kind of concentrated by surface energies into these long strips. And this is why it forms in this zebra stripe-like pattern. Wide bands or narrow bands depend on kind of exactly what the temperature is and how quickly it's cooling. But it's the same process, whether it's wide band or narrow band. So the other key important thing to understand is with a larger delta T, meaning the bigger the difference between whatever you're using to cool and the eutectoid temperature, if you're using air, if you're using oil, if you're using water, any of those things, the bigger the delta T, right? Especially if you're something like, if you're closer to that temperature, your delta T is if the cooling temperature is 675 from 727, your delta T is smaller. That means it's going to take a lot more time for the perlite to grow. If you cool at 650 instead of 675, the delta T is a little bit larger, so you cool a little bit faster, so a little shorter time. It's even more aggressive if you cool at 600 and so on. So the more delta T there's a much more aggressive formation of perlite, and it happens a lot faster, but it's always about trying to minimize the energy between these phases, and that's why it forms these stripes in a fairly straight pattern. So it's a consequence of the thermodynamics that's involved. So the higher temperatures typically are more coarse perlite. The finer temperatures, if you get it cooler faster, it's going to be a little bit less. We'll see that on another graph because of the way that this works. So depending on where you're crossing this cooling curve, the higher the temperature where you're entering perlite formation, the larger perlite grains you're going to have. The cooler you enter it, the smaller the grains are going to be. The reason being, you're spending over here, if you're waiting, because this is a log scale, the farther up you are, the longer you're taking in the perlite region, the more you're going to have a tendency to grow large grains. Here, you're spending a lot less time, and that gives you the result of having a bunch of small grains because they don't have time to sort of grow together and continue. So these are more useful, and this is really what it looks like. So your transformation time is very short here, so they don't have time to grow the much longer grains of perlite in the same way. So moderate cooling curve is going to have what's called normalizing versus a slow cooling curve, which is annealing. So you'll hear Dr. Wright a lot of times talk about annealed steel and things like that. Large perlite grains have been heated and cooled gradually. More severely cooled is going to have finer perlite versus coarser perlite. Coarser perlite is softer. The finer perlite is a little bit harder. Again, generally small grains, much harder than coarse grains. Coarse grains makes things really soft, really pliable. There's also a critical quenching rate. So that's a great thing to say 7 times fast on one coffee. But what you want to pay attention to is where this lands. So it's right at the edge of this phase boundary where perlite starts to form. And this critical cooling rate is you have to stay below this curve in order to reach complete formation of martensite, complete conversion of martensite. If you go above that at all, you're going to have a mix of martensite and perlite. If you go above that, you're going to have ultimately just perlite, and probably some, you might have some other materials as well. So this is what the critical curve looks like. There's a couple more things that we'll need to look at. Let me grab this so we can get a little bit into 11 since we don't have a ton of time. But I want to get you guys as far as I can. So heat treatment, fabrication techniques, these are the things that we're going to be talking about, and really understanding better steel versus iron. So we've talked a lot about the lower end of this curve. So now we can spend a little bit more time talking about the upper end. Real quick, why do you guys think it's important to know where that eutectic point is? What's uniquely useful about this point in the phase diagram? What's unique? What things can you guys identify? So
it's the only point. It's
Go
the
ahead.
only point when you could go straight from liquid to both compositions of both solids.
Yeah, so it's the lowest point because it's the eutectic. It's the lowest point at which the material is completely 100% liquid, right? Where would that be useful? What kind of forming process?
Casting?
Exactly, casting. So what do you guys think material-wise, what range is this? If this is like iron all the way at the left side and there's low carbon steels here and high carbon steels here, what do you guys think goes here?
Medium carbon steels?
You might think medium carbon steels are here, but this is actually the cast iron region. So this is irons that we cast because of their lower melting temperature. So they don't tend to have nearly the same ductility because they have way too much carbon, because we talked about some of that in the grain structure. But we have ferrous materials, and we have so we have iron on the left side, which is just pure alpha ferrite. We have steels below about 1.4 weight% carbon, and then high carbon steels up to typically 2 to 3%, 2 to 3 weight%. Above 3 weight%, 3 to 4.5 are cast irons. So the reason being lower melting temperature. So these are easier materials to cast at 1150 C versus all the way over here at 1600 C, right? Imagine trying to get a wood burning fire furnace up to 1600 C. You can get there, but you got to keep feeding it wood. That's a lot of energy to heat something up to 1600 C. I mean, really a lot of energy to keep and hold it at those kinds of temperatures. That's frankly still hard to do today, especially safely. Hundreds of years ago, very, very, very hard to do. So cast irons are cast for a reason. They have a lower melting temp. And it's just a couple hundred degrees above some of the processing temperatures for certain things in steel anyway. So you're not going to find a lot of cast steels typically because of this additional energy requirement of that extra few hundred degrees C. It's just not worthwhile. And you get a weaker material out the other side in terms of ductility. So why would you want to do that? That would be bad. So that's why we don't do that. But cast irons have ferrite and then sometimes pure graphite as well as cementite. So you start to get just pure carbon forming in some of these. And that's why when cast iron breaks apart, like there's all this really dark carbony black dust, and why when you handle raw cast iron, it has all of those staining properties. It's because it's pure carbon. So it's a really important chart to understand. This is probably all we've got time for today. The low alloys versus high alloys. Plain steels are going to be a lot of these 10 series. They're simple, fairly low, typically weight% carbon. They can be higher weight% carbon, but something like a low value. The first number is indicating which series, whether or not it has alloys. So 10 is just steel, nothing else. So it's iron and carbon, nothing else. 40 series, 50 series, 41 series. All of these are HSLA is high strength, low alloy. So lower contents, smaller percentage still of weight% carbon. So 4310 is stronger, but still compliant. And so structural steels are more commonly going to be these. So high strength, but low alloy, some corrosion resistance, etc. Bridges, towers, pressure vessels, air tanks, all those sorts of things are going to be in this region. So relatively inexpensive compared to higher process materials, stainless, all of those things. So still in the plain series, higher carbon content. This is starting to get into medium carbon steels are a lot of more tool applications. So things that have to take more abuse. Higher carbon content, need to be a little harder. Shafts, bolts, hammers. This is why I said you want to be able to have some non-equilibrated or high hardness materials like bolts, fasteners, and things of that nature, so that they can be under stress in an axis where they're strong, like in tension, for instance, in order to hold together those flexible materials and keep those joints together with high strength, but while still benefiting from the flex of these lower alloy steels. So you blend some of these things. Hammers, blades, 1040 is fairly common for those sorts of things that need to take abuse. A lot of like machete type blades, stuff that's going to be living in a high impact region are going to be probably more like this. Some wear applications are these kind of heat treatable alloys. So 4340 is a good example. Very high degree of hardenability, very good tensile strength. It will not do very well in terms of percent elongation. So percent elongation is where you're going to see changes in behavior under load, and that creates some issues. Higher carbon plain steels are also hardenable. They have good tensile strength, but they're bad in applications where you're going to be stressing them, putting them under tension. So you really wouldn't want to make bolts and things out of these materials. So similarly, you wouldn't want to make bolts out of high strength, low alloy, because they're not really good under tension, and you definitely don't want to make them out of the plain steel, which is not so great in terms of tension, right? Imagine the bolts in your engine just stretching a little bit more and more and more each time you drive the car. Eventually, all of the gaskets would stop leaking or start leaking. You would lose compression, you would lose fluids and all sorts of things. Like, that would be terrible. Nobody would want to design it that way. So we don't use those materials for those applications. Even though it seems like, well, it's all made out of steel, what's it matter? Actually, it matters a lot. The right steel for the right job is really important. So these, because they have a higher degree of hardness based on just the weight composition of carbon and the fact that they're going to have more martensite, they're going to have more fine grained perlite, good in tension strength, not awesome because it's still a plain steel, is hardenable, not good in terms of percent elongation, but because of that higher hardness and that compliance in tensile strength, they're not going to be as brittle, so they work really well in wear applications. So things like disc brake rotors, you want to be in that kind of category. So it's plain steel, but it's not so soft. It's not so soft that it's going to be just eroding at a very high rate. So high hardness material like that works really well. Then you really get into tooling and chromoly, chrome vanadium, tungsten steels, 4190. So much higher in terms of weight percent carbon. Still an alloy, a lower degree of alloy, very high degree of hardenability. Very good in tensile strength, very bad in shear and applications where they need to have lots of load applied. So like drill bits, if you side load a drill bit, what's it do? It explodes. It does bad things. Saw bits. Saws are really need to be a very high hard degree cutting edge. Dies, things for molds, all of those sorts of things. Dies for extrusion, the processing of other materials, the processing of steels has to be that way. So and then the stainless at the very top of the range, high alloy, high corrosion resistance, widely varying hardenability. This is why a lot of those low stainless kitchen knives are just straight garbage. You can't sharpen them. You sharpen them, then you cut a tomato and it's dull again. It's ridiculous because they have different alloys. They can't be hardened or they don't harden them at all. They just want them to be pretty and shiny. Percent elongation is actually pretty good, but really high temperature applications because of the corrosion resistance, because of the alloy components. So they can be often something like 11% chromium in some of the cases or more, and that really helps to prevent corrosion. So we're about out of time for today, so I'll stop the recording here. I know some of you will have to get to other classes and all of those things. Any questions that you guys have?